let's talk about integration more. Let's talk about area under the curve. Like, let's say I want to find, so I just want to remind everybody that when we write this symbol, like for example, the integral from 0 to 6 of the absolute value of x minus 2 dx, when you look at that, what you should see or think is, oh, they're asking me to find the area under the curve. This curve, y equal to the absolute value of x minus 2, between these two x values, x equals 0 and x equals 6. But that's all that this really means. It's just a definite integral. It's definite because we have limits of integration. And it's asking us to find how much area is under the curve. So what I'm going to do this way is we don't have, in fact, even if we did have, which we'll talk about later today, the fundamental theorem of calculus, you still wouldn't use it here because it's a pain. So when you're asked to find the area under the curve, unless someone specifically says you have to do it this way, you should do it whichever way makes the most sense. In my opinion, the way that makes the most sense here is to draw a picture. I can certainly draw the function y equals the absolute value of x minus 2. It looks like a V shape. The bottom of the V is when x equals 2. And when x equals 2, y is going to be 0. And then it's going to look something like this. Specifically, it'd be sensible of me if I were to plug in the x endpoint values to find the y values. So if x were to equal 0, y is going to be equal to the absolute value of 0 minus 2, which is just 2. And if x is equal to 6, y is going to equal the absolute value of 6 minus 2, which is just 4. So the point of drawing this picture is that we see a shape or a graph where the area under that graph takes the shape of a figure that we should know how to find the area of. I've got two triangles, and I can certainly find the area of this by saying it's the area of the first triangle plus the area of the second triangle. And to find those areas, I'm just going to use the triangle area formula, which is 1/2 base times height. So that first triangle, the base, well, again, that's at 2 right there. So the base is a length of 2. The height is also a length of 2, and I have to multiply by 1/2. So 1/2 my base times my height. For the second triangle, similar kind of thing happens. The base is how much? Yeah. I'll put the 1/2 in front this time. And the height also happens to be 4. That's actually a pretty normal thing that happens when you're doing an absolute value of x plus or minus something, is the height and the base of your triangles happens to end up being the same. It's not like a coincidence. It actually usually happens. But either way, we end up getting 1/2 times 2 times 2, which is going to be 2, plus 1/2 times 4 times 4, which is going to be 8, which ends up being 10. So the answer to this question, what's the integral from 0 to 6 of the absolute value of x minus 2, is just 10. It's how much area is under the curve and above the x-axis. I'm gonna try to stop asking if you have questions, not because you shouldn't ask them if you have them, just because I don't even say you have any questions. If you have questions, you should ask them. So if you've got a question, ask them. I'm going to keep moving along here. So definitely stop me if you have a question. I still feel like I should say, do you have any questions? Maggie, yes.
This is not related to this.
Cool.
But will you go over ESO potentially?
Probably not today, but we can probably start talking about it on Monday. Yeah. So here's one of the, in my opinion, issues with the 17B class is they treat all the methods of integration, for which there are many, as like one section in the textbook, whereas like other calculus courses treat it as like a whole chapter of a textbook where you talk about the various methods of how you integrate functions. So we will try to dedicate as much time as we can, because I think it deserves at least a week's worth of time. We'll see how much we can dedicate to that before we have to move on to something else. Certainly we can always backtrack, right? We don't have a set agenda here. I'm just trying to keep pace with what's going on in your actual class. So if we need to go back to look at something or forward look at something, that's totally okay. But we should talk about fundamental theorem stuff before we get to the U substitution stuff. All right, let's look at a couple more examples in this vein, and then we will start talking about the fundamental theorem of calculus. So let's look at 2 more examples, maybe at least 2. Let's say I want to find the integral from negative pi over 2 to pi over 2 of sine of x dx. And again, I'm going to draw a picture. The sine function looks like this. The important point I think of when I graph sine is like when x is pi over 2, or pi, 3 pi over 2, or negative pi over 2, or negative pi. And sine of 0 is 0, and sine of pi over 2 is 1, and sine of pi is 0, and sine of 3 pi over 2 is negative 1. And sine of negative pi over 2 is also negative 1, and sine of negative pi is 0. So here's what the sine function kind of looks like. Oops, except I didn't do a very good job of drawing it there. And it's a periodic function, meaning it just keeps on continuing to have the same behavior every 2 pi, it repeats itself. So I'm trying to find and I'm going to be very explicit here, the net area under the curve that is above the x-axis. So anything that's below the x-axis gets counted as negative. So if we look at this, we're going from negative pi over 2 to pi over 2. So we're getting, hey Lala, we're getting this area over here and this area over here. But as you might notice, the blue area is under the x-axis, so it's going to get counted as negative. You also might notice there's some symmetry here. The blue area and the red area are the same amount of area, just one's positive and one's negative, so they're going to cancel each other out. So what you can see here is that we're just going to get 0 because the blue area being negative cancels out the red, which is positive. And this actually points to a bigger idea, which actually comes up frequently, I would say. And this is the idea that if you take the integral from negative a to a of an odd function, f of x is odd. Not meaning strange, meaning specifically it has odd symmetry. If you rotate this graph 180 degrees around the origin, it still looks the same as it did originally. That's the hallmark of being an odd function. Some good examples of odd functions are f of x equal to x cubed, f of x equal to sine of x, f of x equal to tangent of x, f of x equal to, I'll give you one more, x over x squared plus 1. All those are odd functions. If f of x is odd, then the integral from negative a to a dx is always going to equal 0. Because the area on the left side and the area on the right side will cancel each other out. It's kind of neat. In case you're curious, f of x is odd if f of negative x is equal to negative f of x. So I will point out, because I think it's worth pointing out, I don't think to move this off the page just yet here, that sometimes you might see a question on a test that looks heinous. Something like the integral from negative 10 to 10 of, I don't know, x to the 4th times tangent of x over x squared plus 9. And in all likelihood, especially since I just made that up off the top of my head, it's very, very plausible that you cannot actually find the integral of that. There's a lot of functions actually that are just not integrable or antidifferentiable. What that means, well, what that really means is we should take the hint. The hint being that we're going from a negative number to the same corresponding positive number. So really we should think, oh, maybe the function that we're looking at is odd. But if you're faced with something like this, you probably actually have to show it's odd. So how do you show it's odd? You look at f of negative x and you look at negative f of x and you hope they're the same. Now this is going to require one extra piece of information, which we will say. If you look at negative f of x first, even though I know I wrote the other one first, it's just a negative slapped onto the whole thing. Negative x to the 4th times tangent of x over x squared plus 9. Something to be aware of. When you multiply a fraction by -1, we don't multiply the top and bottom by -1, because that'd be actually multiplying by +1. You can multiply excuse me, either the top or the bottom by -1, but not both. But I'm not going to do either of that until I really know which one might make more sense. So I probably won't actually do it at all, to be honest. Let's look at f of negative x. So f of negative x is going to be negative x to the 4th power times tangent of negative x over negative x squared plus 9. And I should maybe give myself some separation here. So simplifying that, when you have a negative x to an even power, you end up with positive x to the because you have negative x times negative x times negative x times negative x, which is positive x to the 4th. And now here's the thing that we need to know that I actually just said a minute ago. Tangent of x is an odd function. It is a known fact. If you look at the tangent graph, it is kind of funky. If you rotate it 180 degrees, it does look like it looked originally, although it's weird because you've got all these vertical asymptotes, but it totally works out just fine. That means the tangent of negative x meets this criteria, that f of negative x is equal to negative f of x. So tangent of negative x is really equal to -1 or just negative tangent of x. Now I should point out that's not x to the 4th minus tangent, it's x to the 4th times negative tangent. And then on the bottom I have x squared plus 9. And look, that's exactly equal to negative x to the 4th times tangent of x over x squared plus 9. So now we've shown that f of x is indeed odd. Therefore, we can confidently state that the integral from -10 to 10 of that gross looking function has to be 0. Because I don't know what this function looks like. Oh, and that, okay, so I was making a dumb mistake when I wrote this, but I ignored it anyway. I've made a dumb-ish mistake. It's not a huge deal, but it's kind of a big deal because technically tangent isn't defined on this whole entire interval. There's a lot of places where tangent is undefined. So this is not a great question. I apologize. I should have maybe made it like 1/10 to -1/10 so that the interval is defined. I apologize. That was my mistake. In any event, if we make it so it's a defined interval, and so the issue here, right, is that if you think about the tangent graph, you have vertical asymptotes like -pi/2 and pi/2. So the function starts being undefined. You can't really integrate a function that's undefined on the interval. So, okay. But if we have a nicer interval where I know tangent is defined, and tangent is definitely defined between -1/10 and +1/10, then we can say that this interval is 0 because this odd function looks something funky like, I have no idea what it looks like. I'm making stuff up, but it does something like, I don't know. And then it does the reverse thing over here. So maybe that, and then all this area over here cancels out with all this area over here. It's supposed to look symmetrical. I would say it looks semi-symmetrical. So that's the idea with odd functions. Is you have the integral from negative number to this corresponding positive number, and the function you're integrating is odd. You can just jump straight to saying, oh, I get 0. And so if you see something where these are opposites of each other, that is a clue often. That you should be like, oh, maybe I'm just going to get 0. You still have to check that the function's odd, but a lot of the times, especially if the function looks really, really stupid, that means you should try that.
I think it's an issue where even though like for a certain function, even like they correspond, the numbers correspond to each other, they might not.
Oh, totally, 100%. Yeah. You could have something very, very different, like the integral from -2 to 2 of x to the 4th plus 2x plus 3. This doesn't write that. That's definitely not an odd function. So we can't say it's equal to 0. Here, you would have to use the fundamental theorem of calculus. Well, you wouldn't have to. You could do it the long way. The long way would be terrible. Well, let's go ahead and jump to the fundamental theorem of calculus. So here is an example of actually what's called the second part of the fundamental theorem of calculus, which is that if you're trying to find the area under a curve between two endpoints, here's the process. We find the antiderivative of this. So the antiderivative of x to the 4th is x to the 5th over 5. The antiderivative of 2x is 2x squared over 2, which is just x squared. And the antiderivative of 3 is 3x. And don't worry, we're gonna circle back around. We're gonna go back and kind of talk about what leads up to this. But after you find the antiderivative, and it really doesn't matter which one you find, it could be all this plus 1, plus 3, plus c, plus 0. You evaluate it at the upper limit and at the lower limit, and you subtract the difference. You always plug in the upper limit first, then subtract and plug in the lower limit second. So I'm not going to do a whole lot of simplifying here. I'm just going to write this as 2 to the 5th over 5 plus 2 squared plus 3 times 2 minus negative 2 to the 5th over 5 plus negative 2 squared plus 3 times negative 2. And we could simplify that more, but that's not really the point at this juncture. The point is that's how you evaluate a definite integral, by anti-differentiating the function that you're integrating, also known as the integrand, and then plugging in the limits of integration. Top one first, minus bottom one second. Questions about that? And don't worry, we're going to go back and talk about how we get there. Next, we're going to talk about the first part first. All right, so let's circle, and yeah, that clock is really like, the way that light hits that clock is not a good angle for me. It's really hard. I mean, the time is literally written right here as well. I should just look here, but it just feels like, I'm like, oh, what time is it? Okay, so let's go back and ask a very different question. What do I want to see here? Sure, we can do that. I can do that. Let's do that instead. Sorry, there's one example I really want to get to here. Yeah, sure. So let's say I want to find the integral from 2 to x of t cubed dt. I want to find the area under the curve. I've always picked this curve that I'm never good at drawing. T cubed, just like this, from 2 to some x value. So I'm trying to find this area. And even though it's kind of cheating, we're just going to use the fundamental theorem of calculus that we just talked about. So we're going to find the antiderivative of t cubed, which is t to the 4th over 4. And we're going to substitute in our upper and our lower limit. So I'm going to get x to the 4th over 4 plus 2 to the 4th over 4. It's not really necessary, but I'm going to simplify this just because it makes it look a little bit nicer. It's x to the 4th over 4. 2 to the 4th is 16. 16 divided by 4 is 4. Okay, but now here's what I actually want you to see. What happens if we take the derivative of this? What's the derivative of x to the 4th over 4 plus 4? Wow, what's the derivative of x to the 4th? Right. So here's a fun fact. If you have something divided by a constant, it's really the same as multiplying by the reciprocal of that constant. So we really have 1/4 times x to the 4th plus 4, and you get 1/4 times 4x cubed, the derivative of x to the 4th, and then what's the derivative of 4? So I end up with x cubed. And it is not at all a surprise that we have x cubed here, and we started with t cubed there. Those are the same by design. Because what have we really done? We've done two things that undo each other. We did an antiderivative, and then we did a derivative, and we ended up back where we started essentially. Yes, the name of the function is slightly different, right? It's x cubed instead of t cubed, but that's okay. It's supposed to be that way. So here's the real gist of what's happening. If you take the derivative of the integral from some constant to the variable x of some function of t dt, you're doing two things that undo each other. You're anti-differentiating, you're getting a function of x minus a function of a, and then you're differentiating and you're getting back to the same function, but now of x instead of t that you started with. And this is called the fundamental theorem of calculus part 1. No one ever writes out fundamental theorem of calculus. They just write FTC because it's a lot of things to write. Questions about this particular thing. We're going to do some more examples, but I just want to ask if there are, I know I said I'm a liar. I can't not ask if there are questions. So questions about this stuff. Okay, so here's the real point of this. You don't have to do both steps. You don't have to do the antiderivative and then the derivative to find the answer is just the function you started with. You could some of the time. So for example, if I said, what's the derivative of the integral from pi over 4 to x of cosine of t dt? The short answer is just that the answer is cosine of x. And no one wants you to show any work here. Unless they specifically say show some work. Question.
On like a midterm or something.
No, the expectation for this kind of problem is that you were applying the theorem, the fundamental theorem of calculus, and just saying, I know that if you do the derivative of the integral, you get back the function you started with. Let me finish this example, then we'll expand on that. So if we actually did it the long way, even though we don't normally, you would do the inside part first. So when you're finding the integral here, you're getting, well, the antiderivative of cosine is what? Sine, positive sine. And we're evaluating between pi over 4 and x. And then if we plug in, we get the derivative of sine of x minus sine of pi over 4. I'm not going to simplify. I know, okay, sine of pi over 4 is the square root of 2 over 2. We don't need to know that for this process. What's the derivative of sine of x? Right. What's the derivative of sine of pi over 4? Be careful here. It's kind of a trick question. Let me ask you a different question. What's the square root of 2 over 2? Let me ask you differently. Is the square root of 2 over 2 something that changes or something that doesn't change? Like if you plugged it into a calculator, would you get a different number every time you did it? No, you get the same. You get about 0.707. And if something is a constant that never changes, what's its derivative equal to? Right. Another way to say this to yourself, if you don't like what I've just said, is, are there any x's there in sine of pi over 4? No, there's no variables there. And the derivative of something that doesn't have any variables is the derivative of a constant. And the derivative of a constant has to be 0. So look, we ended up exactly where we thought we should, that the derivative of the integral of cosine of t from pi over 4 to x is, of course, cosine of x. Now, here's another reason why this is super useful. Sometimes, actually a lot of the time, the function that is in the integral, the integrand, is not something that has an antiderivative. There are a large swath of functions that do not have an antiderivative. It's unfortunate, but true. A couple common examples, just so you're aware of them. Probably the most notorious example you will see is the integral of e to the t squared, or the integral of e to the x squared. That function cannot be antidifferentiated. There is no function that if you take the derivative of it, you get that. It's kind of disappointing, but it's true. So if I said, I want to find the derivative from 1 to x of e to the t squared, I couldn't do it the long way. There is no way to antidifferentiate that and get something and then plug in x and take the derivative. So we just have to appeal to the fundamental theorem of calculus and say, well, I know the fundamental theorem of calculus works, that the derivative of the antiderivative of a function is just the same function, but with the x variable instead of the t variable. And it works whether or not there's only one t in there or there's many t's. For example, if I want to find the derivative of the integral from -5 to x of something gross looking like cosine of t squared over t to the 7th power plus 9 dt, odds are that's probably not something you can find the antiderivative. I don't know. I just made it up. It might be if you did some weird stuff, but it's probably not. Yeah. But we don't need to because we're not being asked to anti-differentiate. We're being asked to find the derivative of the antiderivative, which is just cosine of x squared over x to the 7th plus 9. Done. No plus c, no nothing, right? Because we took the derivative of the plus c ends up being 0. Okay, there's two other things we should say about this fundamental theorem of calculus part 1, which is, first of all, what happens if I want to find the derivative of the integral from x to 4 of t cubed plus 7 divided by t dt? Now the x is in the wrong spot. I definitely can just make it negative. So you can show the work, and it's not terrible to show the work. You can say that's the same as the derivative of the negative of the integral from 4 to x of t cubed plus 7 over t dt. It's also totally fine to skip that step and just say, oh, I know that when the x is in the bottom, it's going to be the negative of what it should be. So we're going to get negative x cubed. I should put parentheses around this. Negative x cubed plus 7 over x. It's kind of cool. Okay, that's the not so terrible one. The other thing we have to be aware of is sometimes the variable thing, the x here or the x here, isn't just x. It could actually be any function of x you want. Let's look at another example. Let's say we have, I want to find the derivative, and I'm going to make this one that we know how to do. So let's do that. Yeah, let's do that. The derivative of the integral from 4 to x to the 3rd of secant squared of t. And we are going to do this one the long way because we can. So let me ask everybody to think internally for a second. What's a function that if we take the derivative of it, we get secant squared? It's a trig function for sure. And that's the derivative of secant. I want the function whose derivative is equal to secant squared. Tangent it is. The derivative of tangent is equal to secant squared, which means that the antiderivative of secant squared is equal to tangent. So ignoring the derivative part right here, actually just writing it again and covering it up. The stuff in the brackets here, the antiderivative of secant squared is tangent of t. Bless you. Evaluated from 4 to x cubed. Just a personal note here, when you say the integral, you should always, if it's a definite integral like this, you should say the integral from the lower limit to the upper limit. So the way you should say it is the integral from 4 to x cubed of secant squared of t. It's not a huge deal, but it's good to say it right. Great, now we're going to plug it in. So we're going to get the derivative of tangent of x cubed minus tangent of 4. And now when we take the derivative, we have to use the chain rule. So the derivative of tangent of x we know is secant squared of x because of the work we just did, right? The antiderivative of secant squared is tangent. The derivative of tangent must be secant squared. So the derivative tangent of some stuff is going to be secant squared of the stuff times, right, the derivative of the stuff minus, what's the derivative of tangent of 4? Thank you. So we get secant squared of x cubed times the derivative of x cubed. More generally, here's our rule. If you have the derivative of the integral from a to not just x, but a function of x, call it g of x, of f of t dt, well, just like here, we plugged in the x cubed for t, and then we multiplied by the derivative of x cubed. Here we would plug in the g of x for t and then multiply by the derivative of g of x. That's the chain rule version of the fundamental theorem of calculus. So what kind of is interesting to me, having taught math for many years, is this is actually the more important part of the fundamental theorem of calculus. And this is the part that actually has the meaning that says, oh, differentiation and anti-differentiation undo each other. That is really what this theorem says. I know we've been saying it for a while that these two processes undo each other, but this is actually the real meat of this theorem. But it's the second part of the theorem that we actually use the most in this class. The second part tells us that you can do the integral and plug in the endpoints to get the answer. So that's actually the part that we all use more, but this is actually the real meat of what's going on here, which is kind of interesting in my opinion. Let me all have you try one. So, and I want you to do this the short way. So not finding the thing. I want you to find the derivative of the integral from 1 to x to the 4th power of what, James? Of sine of t squared minus 2. Try that. And you don't have to do any, in fact, you can't do any anti-differentiating here. You're just going to use the theorem that we'll put back up there so you all can see it. I'll give you a minute-ish. It looks like you need to go. It's okay if you do. It's okay, you're welcome to stay too. You look like you're ready to go. So yeah. Okay, it's cool. I see. I see all. Well, let's see if I remember people's names. Lalo, Tasia, Dana, Leilani. Yep. Maria. Is that right? Okay. Clarissa, Tiffany, Ashley, Elizabeth, Jesus, Maggie. I should know your name. Andrea? Yeah. Okay. Casey. Cool. All right. It's easy now. We'll see how Monday goes. Also, there's really like 50 people in this class. Yeah, Jesus. Oh my God. I'm sorry. It's a J name, and I totally said it. What is your name actually? Jorge. I'm sorry. I was so confident too. Jorge. Apologies. So again, we're not doing the anti-differentiating here. We're just saying, I know that I'm going to sub in x to the 4th for t and get sine of x to the 4th squared, which we should write as x to the 8th minus 2. And then we're going to multiply by the derivative of that because of the chain rule. And then, yeah, we could write this as sine of x to the 8th minus 2 times 4x cubed. And that's as simple as it gets. Okay, one more, and then we'll talk about the other part of the fundamental theorem of calculus. Let's say we wanted to find the, let's write it this way. Let's say we've got y equal to the integral from, let's make this extra funky. E to the 3x to the natural log of x. So now they both have x's in it. So it works just the way you think it would end up working. You're going to do the top part. You're going to plug it in. You're going to multiply by the derivative of the function because it's not just x. And then for the bottom part, we're going to subtract. And then do the same thing for the bottom part. If you really wanted to, you could break this up as like the integral from e to the 3x to 0 of your function. You don't need to do this though. Plus the integral from 0 to the natural log of x of your function. And then this one would be, if you take the derivative of it, it'd be your function, plug in natural log of x times 1 over x. And then this one, you'd have to change the sign because the variable thing is in the wrong spot. So you'd have this one minus that one, which is exactly what we're saying we're going to get. But let's not do that. Bless you. Let's say we're going to find dy dx. Right, I didn't actually write the derivative yet. I just said this was y, but now we're going to find dy dx, or if you prefer, y prime. And we're going to get the square root of 1 plus the natural log of x quantity squared. I know some people write that as natural log squared of x. Like people write like sine squared of x. Not a fan, but it's fine if you write it that way. I guess it's technically correct. Times, what's the derivative of the natural log of x? Ooh, I know, it's been a while. It's 1 over x. Minus, now we do the other one. The square root of 1 plus e to the 3x squared times the derivative of e to the 3x. And the derivative of e to the 3x, we have to use the chain rule again. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. Okay. I will fully admit I didn't really give you a very definitive proof of the fundamental theorem of calculus part 1. It's not really, I mean, I could. It's not really my role, though. I don't feel like that's super helpful. Hopefully you've seen it in class, but even if you haven't, it's more about being able to execute this process than having someone have shown you the proof of it. That said, if you want to see the proof of it, I'm happy to show it to you in office hours. I just don't think it's like the best use of our time. Questions about this one? I can help myself. Or not Jesus. Okay, all right. Let's talk about the second part of the fundamental, the more used part in this class of the fundamental theorem of calculus. And I wrote myself some notes here. Yeah, let's do that. So here's what we've got. We just said from the fundamental theorem of calculus part 1 that the derivative of the integral from a to x of f of t to t is equal to f of x. And like I've said probably too many times already, if the derivative of something is equal to something else, then the original something here, this integral from a to x of f of t dt, should be equal to the antiderivative of f of x. Let's call it capital F of x. So I should point out, right, capital F of x is an antiderivative of little f of x. And I explicitly use the word and because there are multiple antiderivatives. Right? The antiderivative of 2x is x squared, or x squared plus 1, or x squared plus 7, or x squared plus any constant that you want. So we're going to tap on a constant here. Everyone good with this so far? Okay. So now we're going to do two things that are kind of sneaky. We're going to abuse the meaning of this. All this means here is the area under the function f of t between a and x. So if I replace x with a, I can say the integral from a to a of f of t dt is equal to f of a plus c. But now somebody tell me, what's the area under the curve of f of t starting at a and ending at a? Right. Which means that constant, I can solve for the constant here and get that the constant is equal to negative capital F of a. Cool. So now here's where the magic happens. Let's find, what about the integral from a to b of f of t dt? Well, we know the integral from a to x of f of t dt is equal to f of x plus c. I'm just replacing the x with b, so I'm going to get capital F of b plus c. But we just found that the constant is equal to negative f of a. So that's equal to f of b plus negative f of a, or minus f of a, which is exactly what we do when we evaluate a definite integral. We take the antiderivative of our function and we plug in the top limit minus we plug in the bottom limit. And then we decide we don't want to write it as t, we want to write it as x. So what we typically do is then we say the fundamental theorem of calculus part 2 says that the integral from a to b of your function, whether it's a function of t or a function of x or a function of y or a function of, it doesn't really matter what variable you're using as long as you're consistent, is, I'm going to write it in 2 ways. The way I prefer to write it, which is capital F of x evaluated between a and b. It's a pretty standard notation. And then that ends up becoming capital F of b minus capital F of a. And I guess I should write in, although we know this, where it is true that the derivative of capital F is equal to little f. Or in other words, capital F is an antiderivative of little f. Right? When people write this, that's what they're really saying. They just don't want to write all the words. This here encompasses the entire statement. Capital F is an antiderivative of little f. Because if it is, then its derivative has to equal little f. It's just the lazy, fast way of writing it. So that's what we've got now. We've got the fundamental theorem of calculus part 2. This is how you are expected to evaluate most definite intervals. Not all of them, right? Not like the circle we did at the end of last class. No one expects you to find the antiderivative. They expect you to use your geometry skills and see, oh, that's a circle. I've got a half or a quarter of a circle probably. I'm going to use pi r squared or whatever proportion of that I need. But let's look at a few examples before we're out of time here. Let's say I want to find, I should go back to the example we did way back when that I don't remember what it was. I wish I did. Oh, well. Let's say we want to find the integral from 2 to 7 of 2x plus 1. And I will point out, you could do this one geometrically, even though we're going to do it both ways. So just to confirm that this really does work, here's my graph, kind of. If I plug in x equal to 2, if x is 2, 2 times 2 plus 1 is 5. So that point there is 2, 5. When I plug in 7, 2 times 7 is 14 plus 1 is 15. So this shape I've got here is a trapezoid. There is a formula for the area of a trapezoid. You should never memorize it. I mean, I guess you could. I shouldn't say never, but like I would never memorize it. This actual square here, right, has a base of 5 and a height of 5. And this triangle here also has a base of 5 and a height of 15 minus 5, which is 10. So doing this the long geometric way, the area is 5 times 5 plus 1/2 5 times 10. It's somewhat coincidental that the rectangle and the triangle happen to have the same amount of area, even though I didn't draw them that way at all. So that should be 50. I hope. I feel like I've made a mistake, but we'll find out, I guess. It's always worrying when you look at the answer, like, I don't think that's going to turn out right, but it probably does. Let's do it the other way. So I'm going to anti-differentiate this. I'm going to get 2x squared over 2 plus x, evaluated from 2 to 7. And I would encourage you, whenever you're evaluating a definite integral like this, it is worth your while to simplify the thing before you start plugging stuff in. So we should definitely cancel those 2's and say we've got x squared plus x from 2 to 7. So then we get 7 squared plus 7, okay, minus 2 squared plus 2. And we definitely should have some parentheses around there to make sure we subtract everything that's second there. So I really should have 7 squared plus 7 in parentheses minus all of 2 squared plus 2. And that's going to be 49 plus 7 minus 4 plus 2. And that does turn out to be a-okay. That's 56 minus 6, which is 50. So it works, right? Calculating the area using geometry, calculating the area using the fundamental theorem of calculus part 2, both yield the same result, which is reassuring. So that's kind of the whole, I mean, there's a lot more, I should say. That's the gist of a definite interval. You find its area, or I should say the net area above the x-axis that's under the curve by taking the antiderivative of your function and then plugging in the limits of integration. Which time have I got? The other thing I want to say about this is the reason why we associate this symbol, this integral symbol, with the antiderivative. They are kind of inextricably linked to each other, right? You can't kind of separate them. So when someone says find an antiderivative, like if I wrote, for example, find the antiderivative of f of x equal to, I don't know, x cubed plus sine of x minus 4, instead of just writing capital F, what most people would do is they would have said instead, find the antiderivative of x cubed plus sine of x minus 4. The difference between this and what we've been doing is this is what's also referred to as an indefinite integral. There are no limits of integration here. So we use this symbol to mean find an antiderivative because we know that if it were a definite integral, you would start by finding the antiderivative and then plugging in your points. Here we just don't have any points to plug in. So when you find a definite integral, the answer you get is some sort of numerical answer that represents area. When you find an indefinite integral, aka an antiderivative, your answer is a function of whatever your variable is. So here, if we antidifferentiate this, we're going to get x to the 4th over 4 minus cosine of x minus 4x plus c. And we do need the plus c if it's indefinite. So I just want to make sure that that difference is clear. Indefinite integrals are also called antiderivatives because that's what you're doing to find them. Definite integrals, you're using the antiderivative to then help you find the area that is there. And yeah, fine. It's Friday. I can give you 2 minutes back of your lives. He's going to try and throw in another example, but I'll stop. So we'll talk definitely more about this on Monday. I will see all of you then. Have a lovely weekend.